Hi everyone. In this video we're going to be doing the threading on the jack portion of the screw jack. Now threading can be somewhat complicated, especially for new machinists, so I'm going to cover all the basics in it. Things you should look out for, the dimensions when a certain size thread is called out, how to find all this information, and then just a few little handy tricks for things like the thread relief and stuff like that. Now as far as finding the information, a good place to start would be Machinery's Handbook. Now I've got a business card in here marking my spot, but back here in the threading section you've got all these charts that show you every thread known to man and all of the applicable dimensions to them for the different classes of fit. Now if you don't have a Machinery's Handbook and you don't plan on getting one, that's not a big deal. Just go to Google, type in thread specifications, and you should find tons of different charts that show you everything that you need. Now here's our print for this piece. We have our thread here, we've got various other specifications here, but the big thing we're looking at right here is that it's called out as a half 20 UNF 2A. Now in this video we're only going to be dealing with the threads, and then we'll deal with the ball in the next one. Since we don't really have a ton of length this way that's not going to be threaded, I'm actually going to cut this piece a little bit longer. That'll give me just a little bit more to grip onto while I'm threading. Now whenever you have a call out for a thread on a print, it does not conform to the standards that are posted in the chart on your tolerances. What you have to do, you'll see a call out that looks like this, half inch 20 UNF 2A, and you have to go find that standard in either Machinery's Handbook or on the internet. Now if you go to your Machinery's Handbook or find thread specifications online, you'll find these numbers and these three dimensions. Major diameter, like I said, is supposed to be around half inch, but in order to make the thread fit, it's going to need to be a little bit smaller. So they give you a size range from 0.4987 down to 0.4906. Like any other tolerance, you're going to want to aim for the middle, so we're going to be aiming somewhere for 494. Your pitch diameter is actually an imaginary line running down the middle of each thread. So in between the major and minor diameter on one side and the major and minor diameter on the other. Despite the fact that it's an imaginary line, pitch diameter is the most important dimension because this is what determines your class of fit. Now you're going to be measuring your pitch diameter with either thread wires or a thread micrometer. I'll show you both of them. The number you're looking for is somewhere between 0.4662 and 0.4619 for this particular thread. Now unlike most tolerances, you're not really aiming for the middle here because it's very easy to hop over this range. So you'll just take light cuts until you fall somewhere within that range and then call it good. Now your minor diameter is only given as a single number for an external thread. The reason is that you just need to make sure that any chamfer or thread relief that you make is going to be smaller than that number, in this case 0.4392. Otherwise you could end up with light threads in your thread relief, or you would still raise a burr at the beginning of the thread if you didn't cut your chamfer deep enough. If this was called out as a Class 2B thread, you would have a minor diameter range, a pitch diameter range, and then a single number for major diameter, again just to make sure that any thread relief you cut or chamfer that you cut would be large enough. Just like before, the very first thing I'm going to do is touch off on the face, clean it up, and then I'm going to zero that as my Z dimension, and then I'll cut it down to diameter for that 1 inch length for the thread. I'm going to go ahead and use the power feed on my lathe, so I've got it set to about 4 thousandths per revolution. So I'm at 1.107 and looks like 4/10. So I'm going to input that into my digital readout. Now, like I said before, our range for major diameter is 0.4987 to 0.4906. So I'm going to be aiming for the middle of that, 0.494. So I made all of my roughing cuts with an insert that had already taken a fair amount of abuse. I didn't want to use a brand new insert and screw it up, making all those heavy cuts. So I have changed to a fresh insert now. I'm about 50 thousandths oversized, and I've also bumped up my speed to accommodate for the smaller diameter of my part now. So I've got a pretty decent surface finish now. Let's go ahead and get a measurement. Alright. According to this, I'm at 506 and probably about 3/10. Yep. So that means I've got 12 thousandths to take off in order to get to my 494 target. And it's looking like I'm 494 and a little bit of change, maybe about 5/10. Let's see. 4/10. 494 and 4/10. Right smack dab in the middle of our tolerance. So we're ready to put the chamfer on the edge here, and we're going to go ahead and put the thread relief and chamfer on the backside. So I have an old brazed carbide threading tool, an offset one that, the tip had broken in use. So I reground it to be a 45 tool, and I put a 45-degree angle on both sides of center. Really handy to have. I highly recommend you guys do that sort of thing because chamfers are just really quick and easy doing it like this. The print shows the chamfer at 45 degrees and 35 thousandths long. That means once we find this corner, we move 35 thousandths that way. There's my corner. I just brought it in as slow as I could until I got a chip, and now I'm just going to move to 35 thousandths on my digital readout in the Z. There's the chamfer for the end of our piece. I'm going to go ahead and switch to my thread relief tool now. And for the thread relief, I'd like to show you guys the tool that I ground specifically to do thread reliefs. I do quite a lot of them, so I just figured I'd do a dedicated tool. It's entirely optional. But what I've done is basically ground a tool that has my 1/8 inch width there. I've got my 45-degree angle. And then rather than coming straight back here, I've actually given it a little side relief there. That's to keep it from rubbing against the shoulder that you make. So in practice, you would bring it up and touch this shoulder, you would plunge in, and you would create not only your thread relief, but the chamfer on the thread all in one shot. So I'm embarrassed to say that I forgot to hit the record button when I did the thread relief. But basically what I did was I touched off on the shoulder with the corner of the part, and then I touched off on the diameter so that I could zero that. And I did stop shy so that I could actually take a measurement and make sure I was where I was expecting to be. The other thing you need to worry about with this is that your tool has a lot of contact with the part. So it's going to want to chatter, so you're going to want to run it slower than normal. I ran it at about 100 RPM. I still got a little bit of chatter, but not too bad. So right now I'm getting set up for threading, and I'd be remiss if I didn't discuss the two schools of thought here on threading. The first one is to just plunge straight in using the cross feed of the lathe until you get to the depth of your cut. That's pretty simple. It's not very complicated at all. And if you look at your thread gauge here, you can see that it has this chart on it that says the double depth of the American National thread. So if you find 20 there, it tells you would need to plunge in 65 thousandths of an inch. Now that's not the method I prefer because in my experience, you get kind of a bad surface finish. What you get is, if you've got your threading tool there, you end up with a chip coming off of both sides and they collide in the middle, and it seems to just sort of rip and tear the threads. You've got a lot more tool in contact with the material. My preferred method is to make my feeds in with the compound, and the compound is angled at half the angle of the thread. And then I always feed my cross feed back to 0 at the beginning of each cut. So I'll get to the end of my cut, I'll pull out with my cross feed, I'll return, I'll bring my cross feed back to 0, and then I'll adjust my depth of cut using my compound. What this gets you is your threading tool like this, but only one side of it is actually doing all the cutting. This one is taking a very slight skim cut, but since it's feeding in at half the angle of the thread, it's really only cutting on this side of the tool, and you get a much nicer surface finish. So in the textbooks, you'll see 29.5 degrees listed as the angle of your compound. That is somewhat correct. I say somewhat correct because it depends on where 0 is on your compound. On a lot of modern lathes, including this one, 0 has the compound parallel to the lathe axis. So if you move it to 29.5 degrees, you're at the wrong angle. That 29.5 is dependent on the 0 being over here and the compound being perpendicular to the lathe axis at 0. So if your 0 has your compound perpendicular to the lathe axis, the 0 over here, you would have to have it at 29.5 degrees. If your machine has a 0 that puts the compound parallel to the lathe axis, it needs to be at 60.5 degrees. Now we all know that 60 degrees is the angle on our threads, so what's the deal with that 29.5 and 60.5? Well, like I said, that's so that the vast majority of your cut is happening on this side of the tool, but it's still taking a little bit of a skim cut on this side, just to clean it up. And while I've got the camera in this position, I want to point out a couple of things. I'm not going to get into controls too much because every machine is different, but the one thing that you need to find is your half nuts. So this is the half nuts of the machine. They're literally 2 halves of a nut that clamp down on the lead screw, and that's what drives your carriage. The other thing is your thread dial. The thread dial is what you use to re-engage the thread that you just cut, because at the end of the cut you're pulling out on the crossfeed and disengaging your half nuts, and then you return to the beginning, you bring this back to 0, then you wait for one of these numbers on your thread dial to come along to the marker, and you re-engage your half nuts. Now, depending on the threads per inch that you're cutting, you can sometimes engage them at every number, sometimes every other number. It all depends on your machine, but you should have a chart. Mine is right here. You can't see it. But at 20 threads per inch, I can engage at any one of the numbered lines. This is going to be somewhat machine specific, so I'm not really going to get into it a lot. But just look at your thread dial, look at the chart that you have, and figure out what you need to do as far as engaging the half nuts in order to cut that thread. So once you've got your angle set on your compound, the next thing you have to do is make sure that the tooltip is actually perpendicular to the part. Otherwise, your thread geometry is going to be off. Instead of cutting a thread with a profile like this, you're going to end up cutting a thread with a profile like this if you're not perpendicular to your part. Now that's actually one of the main purposes of this gauge. It's not just for grinding your tool, it's also for setting things perpendicular. Now, right now I've got my tool post loose. I can move this dude around, and I'll show you a quick trick. Get yourself a piece of white paper. Your print usually does quite well. Lower your lamp so that it's shining down below your part. Now you can see the silhouette of your tool and your part. And we can bring the gauge in here. We'll crank this over that way. You want to try to get your gauge absolutely flat against the surface to be threaded. Then you bring your tool end to one of the notches and you're trying to get it all lined up. So just like that, you can see that I have my tool lined up and it's perpendicular to my part. All thanks to the nice bright background and the silhouette. Then of course make sure that you tighten your tool post back up. Just like anything else, you need to go ahead and touch off your tool. And in this case, I'm going to touch it off and I'm going to zero both my digital readout and my dial on my hand wheel. Doing both gives you a bit of redundancy, and it's a lot faster to go back to 0 on your dial than the digital readout, because on the digital readout, it's so twitchy, you tend to want to sit there and spend a little bit more time getting it right on 0. So using the digital readout alone tends to slow you down. Let me go ahead and touch off. Alright, there's my touch off. I've zeroed my dial. I've zeroed my digital readout. And I'm also going to go ahead and zero my compound. Zeroing your compound isn't strictly necessary, but if you're cutting multiple threads at the beginning of each one, you can start at 0 on your compound and 0 on your crossfeed, and you'll know how deep to go each time. At this point, I've really dropped the RPM on my machine. I've got it down to 100 RPM. You do not want to thread quickly, because in this case we're cutting 20 threads per inch, which means that each revolution of the chuck, it's going to be feeding 50 thousandths towards the headstock. If you feed quickly, you're going to crash your machine. Generally, I base my RPM off of how comfortable it is to engage my half nuts reliably on the thread dial. If it seems like I'm waiting a year and a half for each of the numbers to come around, I know that my RPM is way too slow. If the marks are going by so quickly that I can't reliably engage my half nuts, then I know my RPM's too fast. The RPM of the machine is largely going to be dependent on the threads per inch or metric pitch that you're cutting. Because if you're cutting 8 threads per inch, you're going to want to go a whole lot slower than if you're cutting 32. One thing that I would highly recommend to people who are new to threading is to cut air first. And what I mean by that is run the machine with your tool way out here so that you're not going to run into anything, you're not going to crash into the chuck, and you can get the mechanics down first. Let me demonstrate. So I've engaged my half nuts. This is what it would be like if you were cutting threads. And at the end of your cut, you always want to pull out your crossfeed and then disengage your half nuts. Now the reason for doing that is because you're not always going to have a thread relief. And if you just disengage the half nuts with the tool still engaged in the work, you're going to end up with a thread relief. Okay, I'm going to go ahead and start. And I've got my crossfeed set at 0. It's also reading 0 on my digital readout. I've zeroed my compound as well. Now I've fed my compound in 10/1000ths of an inch. That's a good first cut. Each successive cut needs to be lighter and lighter because you're getting deeper into the part and you're removing more and more material off that leading edge. I have a second camera set up showing my threading dial as well as my half nut lever, so you guys can see what the timing is like. Okay, here comes the first engagement. So you can see how I got to the thread relief and I pulled out a little bit and then disengaged my half nuts. That allows me to get back to the beginning, and then I can move back to 0 on my crossfeed. Now I just advanced my compound and I'm ready for my next cut. But before I do that, I want to make sure that I actually have 20 threads per inch. And I'm going to come back to the fishtail gauge. So you can see there's actually several scales on this. You've got 24, 32, 14, and 20. You can use those for checking your threads per inch. So I'm using my 20 scale, and I can see I've got a thread at each of the graduations. The nice thing about that is you can also use that for 10. You would have a thread at every 2 graduations. You could use it for 40. You'd have 1 graduation every second thread. And all the multiples. So 14, 28, 7, 32 is very useful. You can use it for any of the factors of 32. Same thing with 24. So I'll put a little bit of oil there. Always helps. And here we go. Now it's very important to note that your threads are not actually going to be sharp at the end. A lot of people will sit there and cut them and cut them and cut them until they're pointy, and at that point you've actually gone too far. With the specs for that thread, that major diameter that's a little bit smaller than a 1/2 inch is going to leave a bit of a flat on the top. Okay, so now I'm going to show you a couple of different ways of measuring. The first way is with a thread micrometer, and this is a very fancy one that has interchangeable anvils that you can use for different thread pitches. And the way it works is you have a pointed anvil and a V anvil. The V anvil is obviously going to go across the crest of a thread, and then the point will go across the opposite root. Now these can be a little tricky to use because it's very difficult to get them centered on the part, on the diameter. So what I do is I'll get the V in at first, and then once I bring the point in, I'll pivot it on the point so that I can feel the high spot in the V. It's a real sense of feel here, and you'll be able to feel very quickly if you're off center because you won't be able to rock it one direction. So we're showing 481 thousandths, and this one doesn't have a vernier scale, but it's about a half a thousandth. So 481 and a half. Now you'll remember from earlier in the video that our range is 4662 to 4619. So we've got quite a bit, but don't think that we need to take off 20 thousandths of an inch. We don't. That V is getting wider and wider as we go deeper, so we don't have to take off that much at all. Thread micrometers are nice because they read pitch diameter directly and you don't have to do any extra math, but they are quite expensive. A much cheaper way to measure threads is with thread measuring wires. Now you can get these in a set for maybe $25 or so, it depends on where you buy them, and they come with a whole mess of different wires in different sizes. So how do we use these? Well, you've got this little chart, and it says here if you're cutting 20 threads per inch, you use the 29 thousandths wire size, which is right over here. And then you've got these two columns. The important one is the constant. The constant is what's going to be subtracted from your measurement in order to see what your pitch diameter is. So in this case, it's 0.0437 inches. So rather than constantly grabbing my calculator every single time I make a measurement with the thread wires, I generally go ahead and write down what my measurement over the wires would be to get my pitch diameter range. So what I mean is, here's our pitch diameter range that we got out of Machinery's handbook, 0.4662 to 0.4619. And then from our chart in the thread wire set, we have our constant for the 29 thousandths wires measuring 20 TPI. That is 0.0437. So that is normally what we would subtract from our measurement over the wires. In this case, I've gone ahead and just added that number to our pitch diameter range. So what that means is our range for the measurement over the wires is going to be 0.5099 to 0.5056. As soon as I'm within that range, then I can stop. Now in using thread wires, you put two on one side, straddling the crest of one thread, and one on the opposite side, and then you measure them with a standard micrometer. Now, I highly recommend cleaning out the chip pan before you use these, especially with the smaller wires, because they are very easy to lose. And one trick that I like to use is I'll put a little dab of grease on the threads so that the two on top will stick, and then all I need to do is handle the one on the bottom. So these stay there because of the grease, and then I just measure across them with a regular mic. The grease isn't thick enough that it's going to affect my measurement, and this way it's also self-centering. Some people will put rubber bands on them and try to measure them that way, but that can pull the wires one way or the other, and we don't want to do that. So right now I'm measuring 522 1/10 over the wires. So I've repositioned the camera off to the side so you can see what I'm doing with the crossfeed dial as well as the half nuts. So let's go ahead and take another cut since we're so small. Now some people might ask, well, the thread wires seem to be a big pain in the butt. What's the advantage to them? Well, like I said, these are quite cheap. I mean, you can get thread wires for just 25, 30 bucks, and you can measure them with any standard micrometer that any shop is going to have lying around. So this doesn't matter if it's 1/2 inch 20 or 2 inches 20. You'll still use the same wires and you'll still use a standard micrometer. Whereas with a thread micrometer, you're going to have one for each range. So you'd have one for 0 to 1, 1 to 2, 2 to 3, so on and so forth. And that gets expensive really fast. Right now I'm showing 517 1/10 over the wires. We're getting closer. My measurement over the wires at the top range is 5099. At this point I'm going to go ahead and take a measurement after each cut because we are getting pretty close. I'll use the thread micrometer on this one. And it looks like we're at 470 thousandths and maybe a tenth or two. It's getting really close. That's only 4 thousandths off the top end of our range. Okay, we are at 466 and probably about 4/10. That's just over the top end of our range. The tricky thing here is that we may accidentally take off too much if we try to advance our tool again. So what I'm going to do is just take a spring pass. I'm not going to adjust my compound at all. I'm just going to move back into 0 on the cross feed, and it's probably going to take a chip. We're taking a pretty healthy chip, and that's a bit of a surprise. And just that one spring pass actually dropped us down to 462 and probably 7/10. And luckily that is within our tolerance. It's towards the low end, but you can see how risky it is taking that last cut. Now some of you out there might be wondering, well hey, why don't we just try this with the mating part? And we can certainly do that. Here it is. It screws on very nicely. We could also try this with a 1/2 nut, and that would also be fine. The problem is that doesn't really tell you if you're too small. It tells you that the upper end is okay, but this thing would screw on there and it would still be rattling around on there. That doesn't necessarily mean it's in tolerance. The other thing people might ask is, why don't you just use a die? And okay, there's plenty of good reasons not to use a die on something like this. A die is very difficult to start straight. It wants to angle one way or the other because of the helix of the thread. And you end up cutting what are called drunk threads, where it starts at a bit of an angle, and as it goes deeper and deeper on a part, it's actually angling this way. So you end up with really deep threads on one side of the part and almost non-existent threads on the other. That also makes the part that's actually engaging the threads engage it at an angle, which is also a bad thing. Now one good use for a die would be to clean this up if you had maybe some tight spots. Let's say it's free here and free at the end, but there's a tight spot in the middle. Well, you could run the die on there and it'll clean it up. In those situations you don't have to worry about drunk threads because it's going to follow the thread that you've already cut. So here's the threading portion of this part done. And in the next video what we'll do is I'll change to a 5C collet setup so that I can grip the threads without damaging them. And we'll go ahead and do the other side. We'll turn it down to 850, we'll do our ball, and that'll be about it for that video. We'll do the milling in a separate video. Thanks for watching, and I'll see you next time.